In Module 14, we will talk about binary search trees. We will talk about what is the binary search tree. So you will see how can we do the searching from the binary search tree. Of course, we still have the push and the pop operation to push our value into the binary search tree. So the push operation actually is the operator square setter function. So then when I want to remove a data, that's we need to delete key. So now you see the key, we will know, right? Binary search tree actually still is an associative array. We have the key and the value paired. To complete the binary search tree, actually we will do the couple recursive operation. So then we'll see how we will do the tree iteration using the recursion function. At the end, we will talk about the tree balance. So of course, we will work on the lab exercise 14 and the homework assignment. So the first thing, let's talk about what is the binary search tree and why we need that. Before we talk about binary search tree, I want to remind you again. You remember before we have the first time to introduce key and the value pair. That's our associative array. So that associative array, when we had the first version, the associative array, to kind of implement the map template library in C++, we're using the kind of like dynamic array. So then we have the key and the value pair. But each searching, no matter we're using for the operator setter function to add a new value, or using operator getter function to get the new value, the value of the element. Each one, the runtime is big O(n). The reason is we need to using a for loop to traverse each element in the array. We are not satisfied with the associative array, the runtime. So that's why in the passing week, we talk about hash table. So this hash table, the same thing. We try to using the key and the value pair, but we improve the runtime. We bring down the runtime from the associative array from big O(n) to the log n. Actually, that's a big improve because log n is kind of constant runtime. So in order to bring down the runtime to the log n, actually we have a couple different solutions. For the hash table, we can using the probing solution. The load factor need to be under 50. The training solution, the load factor need to under 80%. But no matter which solution, actually we all use the static array. So that's why even we bring down the runtime from the hash table, we have couple drawback. The first thing, right, because we use the static array, we cannot adjust the capacity. So once you have your more data to add into your hash table, you possibly will make your load factor cannot meet the requirement. So on the other hand, we need to relocate and double the size of the array, or we call that rehashing. And addition to that, because we have the very low, the load factor we need to maintain the hash table. To maintain the runtime is big O log n. That's why sometimes your array, we need to create the size at least twice as our data have. So that's why we have a lot of space we waste. So right, from the associative array to the hash table, even we improve the runtime, but we do have couple drawback we need to pay attention. So in order to eliminate the drawback from the hash table, but we still have the big O runtime log n. So that's why we bring you another solution. Did you see here your associative array why your runtime is big O(n)? That's because you need to have a for loop to searching for your key. So that's kind of the linear search we talked about last week. We have the linear search and we have what? We have binary search algorithm. The difference between the binary search algorithm is your data need to be sorted. Then we can perform the binary search. We always start from the middle. If the target value we're looking for is greater than the middle, we go to the right-hand side. Otherwise, we go to the left-hand side. So that we can bring down the big O, the searching time become log n. So right, apply for the binary search. We will create a binary search tree to replace our associative array and hash table. They are still provide the same functionality. You provide a key, you provide the associative value. But one thing is, we will have all our data in a sorted order. So that's why we can perform the binary search, and we will bring down the runtime log n. So now we will see how should we have our data being sorted. So to apply the binary search tree, so one thing is we will think about, should I using array or linked list? So right, so we have different two choice to think about. Okay, but one thing is continue. Before we decide using array or linked list, so the first thing, we know we need to have performed the binary search. So that's why we need to have a fast way to right away find where is the middle value. So that's why the middle value should be every time is the first one I can access. Right, so we can calculate the middle index according to our index value. So that's where we were searching for. So this middle value can bring us to help us to go to left or right half. Right, so that's why if your target value is smaller than your middle value, then we need to go to the left-hand side. So that's for the last thing, for the last value. So then the right-hand side is your target value greater than the middle value. That's why we go to the left-hand side. So that's why your left and right is very clear to see. So in order to help us to easier to go to the left and the right, so that's why after we talk about our tree struct last week, the past couple weeks, we will have our binary search actually in a tree order. So actually they will have the hierarchic will look like this. So that's our binary search will look like. So again, let's talk about phone book example. So when you have your phone book, we have the key is your friend's name. Then you have value is your friend's phone number. So according to your friend's name, that's why we need to have the key stored in the sorted order. But the sorted order is what? You see, that's why here, when I have the top of my tree, this one is the middle value. Go to the left-hand side. The older value will be smaller than or equal to the top value. So that's why you see Fred, Carla is start from C, smaller than Fred. So here's the Carla. Carla has the left children and right children. So then you see all the right children from the Carla, actually Denise is greater than Carla. So Alex is smaller than Carla. So on the other hand, now our binary search, we make that become a tree. The first one, we have the root node. So this root node will be the start doing the searching. So then on the left-hand side, all the nodes on the left-hand side from the root node, they will be smaller than or equal to the root node. And all the nodes on the right-hand side from the root node, they will be greater. And also this one will apply for all of them. So then actually every node, your left children always smaller than you. Your right children always greater than you. So that's our binary search tree. So for example, here now if I want to find Mary, do I have Mary's phone number? So then I start from my root node. So Fred, okay, not. So that's why Fred is smaller than Mary. So I go to the right. So then Mark is not Mary. So then we will go to the right hand side because Mary is greater than Mark. So then we go to the right hand side. So then when you see the Luther, so then Luther is greater than Mary, right? So we go to the left hand side. However, if your left hand side have no children, we know Mary is not in our binary search tree. So that's why in this binary search hierarchy, you see the node actually will be the total node n, but the level 1, 2, 3 will be the log n. So that's why every time when we do a searching time, the runtime will be log n. But the second question is, after we have this kind of hierarchy, right? So how should we implement that? Should we implement that in the array or in the linked list? Before, actually, we were thinking about, oh, you have the children. So then we need to have the children index relationship with the parent. But that's because before, when we have our, that's because before when we're using the priority tree, we need to add the new node. We need to try to promote, we need to go up. Or we pop the old node, we will see who to promote. So sometimes you need to going down, going up. So that's why we need to have parent index relationship. But now here is different. We never go up. We always going down. Because when you start the root node, you just need to compare one by one so then you know how to finish. So this one actually will be a little different. We only need to have the relationship is to node. If you are a node, you only need to know your left children and right children. You don't really need to know your parents. So that's why here, instead to using an array, actually this one, our binary search node. So each node, we still have the key value pair, but we only also need to add the left and the right children. So actually they kind of is okay. We can have, they are become a linked list. So that's why here is your binary search node struct. So you have your key and the value pair. So then you have your left node and you have your right node. So I don't need to worry about the capacity. So that's why I only have the size as my private data. So then I only need to have the root node. So that's I will start doing the searching. And also remember your binary search will be exactly you want to have the same interface as your associative array. So that's why here for your binary search public interface, for the linked list version, we will be look like this. So then you see you have your struct node. You have your key and the value. You have your left children and the right children. So we don't need to worry about the capacity. So then you only need to have your root node. So then you have your private data is size. So then right, you will see 3 addition private function. So these 3 addition private function, we will talk about that later because actually user doesn't know that. So we will talk about these 3 function actually is for our recursion purpose. So then so you just kind of ignore these 3 private function. So we just continue to see the binary search tree should have the same public interface as our associative array. So that's why here we have our constructor, default constructor, your root node and the size equal to 0. And of course, because you are the linked list, so you need to have your constructor, assignment operator, and the destructor. So right, I need to know my size. So then right, see here, I need to have my square bracket getter function and square bracket setter function. I need to know, do I contain this key or not? So you have contain key getter function. You have delete key getter setter function. So of course you have your keys. So I can get all the keys in a queue. So then you can clear. So of course the clear will be the same as the structure. So that's why here you will see they have the same public interface as associative array, as the hash map. So of course the next thing we will do is, how should we do this 2 getter function and 2 setter function? How should we implement that?